My talk today is on exploring for different styles of iron ore at Weld Range in Western Australia. I'm talking on behalf of the Iron Research Group at the Centre for Exploration Targeting UWA, and the project was sponsored by Sinus Steel Midwest. The Weld Range area is located in Western Australia in the Yilgarn Craton. It's located to about 700 kilometres to the northeast of Perth, and in the diagram you can see a number of iron ore districts, the Southern Cross, including Coolinobbing and Windarling, the Carrara area in Murchison Domain, and here's the Weld Range deposits up here. So what is the significance of these deposits? Well, it is a small iron ore resource. However, what it does show is it does show very nicely the transitional steps in iron ore formation. So on the left-hand side here, we can see the examples of iron ore exposed in the ridge there, and the ridge continues for about 70 kilometres along strike. On the right-hand side, you can see large deposits in Brazil. And the thing about the large deposits is that it generally preserves, one or two main ore types, whereas the ones in the Weld Range, there's 5 different ore types, and you can see the stepwise upgrade in iron in the banded iron formation. So it's quite special from that perspective. So for the remainder of the talk, I'll quickly outline the geological setting in the Weld Range greenstone belts and talk about its iron deposits. There are 5 distinct types of iron ore within the district, and I'll run through their characteristics, and then I'll conclude by talking about exploration strategies within the district. So where's Weld Range? On the right-hand side, you can see the solid geology map. And in very simple terms, we have greenstone units within the colours, apart from pink being the granitic rocks. And we can see the banded iron formation, which is also known as BIF, in these cyan colours, and they're interspersed with mafic sills and basalts, gabbros, dolerites. In outcrop on the left-hand side, you can see the exposure of the BIF along the ridge, and in between the BIF ridges there's some nice examples of rounded boulders of gabbros. And I will draw your attention to the 2 deposits, the Beebyn deposit in this area here, and the Madoonga deposits along the other margin of the ridges. These are summary maps of Beebyn on the left here and Madoonga on the right, and the top shows what they look like in plan view, whereas the bottom shows the cross-sectional views. Beebyn on the left, showing the area within this field here. This is the site of the future open pit, and in section, if we draw a section round about through here, you'll see there's 3 main banded iron formations, which are separated by the mafic igneous rocks, and you can see the iron ore, the high-grade iron ore zones are located beneath the zone of modern weathering and also occurring near surface as well. So that's quite unusual that these iron ore bodies continue through the weathering profile into fresh, unweathered banded iron. At Madoonga, we see this interesting scenario where we've got 2 BIFs. In this case, it's separated by a volcaniclastic unit on either side of the mafic igneous rocks. Along this southern margin, there is a black shell, and if we just look at the weathering profile, it really is drawn down in this southern area of the BIF, and that's where we have the high degree of shearing, and so near surface fluids have been able to move down this shear zone and cause weathering in the banded iron formation. The other interesting thing is the occurrence of detrital ore along the southern extent of the ridge, and this is probably a paleo channel where materials from the top were distributed down and settled in this topographic low, and that's why we have a lot of banded iron formation clasts fused together within goethite hematite cement. So there are 5 different iron ore types at Weld Range, and this diagram is showing things spatially. So you can see from near surface down to depth and then uncovered again, and it also shows progression through time. So very briefly, you have BIF forming at surface, being buried, undergoing diagenesis and burial metamorphism to form a quartz magnetite BIF. This has been metamorphosed to grenaceous facies within the Weld Range area to a meta-BIF, and around about this time we had a series of deformation events, and you can see how I've matched the different ore types to the different deformation events. The earliest ones coinciding with folding in the area, and then with shearing and uplift, and we have these brittle faults associated with supergene mineralization, and then near surface the formation of these detrital iron ores. How do these look like in hand specimen and thin section? Well, here's an example of the hypergene residual magnetite ore, and this is the unmineralized BIF. So this area here is silica-rich band alternating with iron oxide-rich bands. So how can we remove these silica-rich bands? Well, one way in this example is that these silica-rich bands have been completely replaced by carbonates. There's been some introduction of a hydrothermal magnetite. You can see it peppered with these euhedral crystals, but principally it's a replacement of the silica-rich bands by carbonate gangue minerals. And what this means is that a subsequent fluid can go through this BIF and suck out, remove all of the, dissolve all of the carbonates, and then we have a collapsing of adjacent bands, and we have the residual enrichment of these less soluble iron oxides, and that's how we form our residual magnetite ore. And this is what it looks like in 2 different scales. I guess before we had the scale of hand specimen, this is the scale of the deposit. So again, we have the same field as I showed you before. This is a future area of the open pit, and then we have a number of elements here, and you can see that where we have the high grade iron ore, we have a corresponding depletion in silica, which is the removal of these silica-rich bands in the BIF, and we also have a general correspondence with loss on ignition component. And at about more than 100 meters below surface, we have fresh rocks, unweathered rocks. So the loss on ignition component is most likely caused by carbonate alteration. So here we have an outer carbonate alteration halo and inner areas of silica depletion and high-grade iron ore. And phosphorus generally is associated with carbonates. We see that in thin section and with the scanning electron microscope. So where we have the hypergene carbonate alteration, we've also got the introduction of phosphorus. And on the right-hand side, we have all of the geochemical data for the Beebyn deposits for unweathered material. And hopefully what you can see, I've plotted silica versus iron. So we go from our least altered BIF within this area here, and as we remove the silica and replace it by carbonates, we have it being shifted down towards this area here, so a decrease in silica without a big increase in iron. But as we remove the carbonate, we concentrate the iron, this portion here. And then subsequent hydrothermal fluids have resulted in the addition of contaminants, say the addition of quartz carbonates, sulfide veins, for example, and this has increased carbonates to move our composition back here. So what we found is that this sort of patterns in the geochemistry can very quickly tell us that we're dealing with this alteration history. And if we look at surrounding mafic igneous rocks, here's a least altered example here. You can see the texture is nicely preserved here. In areas proximal to the iron ore, you can see the destruction of the original texture and original minerals, and now it is mostly hypogene chlorite and possibly some talc. This chlorite is iron rich. And what we can see in the geochemistry is that the least altered mafic igneous rocks plot here in the orange field, and as we go towards higher degrees of hypogene alteration, we have a decrease in silica as we replace some of these silica-rich igneous minerals and metamorphic minerals. We're replacing them by more iron-rich minerals. And with the proximal alteration zones here, it's a bit small to see, but generally we have a decrease in silica, and we have also depletions in potassium, calcium, these elements. Now, how does it compare with the second type of mineralization? In this case here we have hypogene magnetite veins, and in this photograph of outcrop I've got my hammer located here for scale, and hopefully you can see some regional banding within the BIF, like so, the alternating silica rich bands and iron oxide rich bands. And then the key thing here is this magnetite rich zone, which is like a fault hosted vein cutting through the banded iron formation at a 45-degree angle. And how this looks in the geochemistry for this area, this is the Madoonga deposit. We can see our least altered BIF plotting here, the same area as Susie in that previous slide for the Beebyn deposits. But instead of having the more complicated alteration pathway, something like that, basically we just have the addition of iron. So we have a straight line movement in the chemistry of BIF towards high-grade iron in this area of the plot. So just the addition of iron through these magnetite-rich veins. Okay, very quickly, third type of iron ore is this specular hematite veins. Again, you can see in the field what it looks like. This is a couple of centimeters thick vein of coarse-grained hematite. Sometimes it also includes hydrothermal quartz intergrown with the hematite, as we can see below in this example of a rock. These nice big blades of coarse-grained hematite intergrown with hydrothermal quartz. So these have come in along fault zones within the BIF, and quite often at a shallow angle to banding. The fourth type of iron ore within the BIF is a supergene style of mineralization. In the outcrop, it's looks a little bit like this. This is near Madoonga, and again my hammer is located here. And you can see the destruction of the banding within the BIF, and now it's quite a mottled texture with cavities, and comprises mostly goethite and hematite. So no preservation of the original texture. And it's controlled by brittle faults, which have let near-surface fluids percolate through the band iron formation, dissolve the silica, and we have a concentration in iron oxides, which are generally the hydrous iron oxides of goethite. Lastly, the last iron ore type is only observed at the Madoonga deposits, as I've mentioned before, around about here, and this is what it looks like in the diamond drill core, with large fragments, angular fragments of banded iron formation, perhaps examples of hypogene iron ore, but perhaps at the very least these are iron oxides dominant, and you can see that these classes cemented by goethite and cavity rich. So in terms of the relative importance in ore types at Weld Range, our two dominant types are the residual magnetite ore, which occurs at the Beebyn deposit, and the second one is this goethite hematite ore, which occurs at Beebyn and Madoonga. And I think the interesting thing at Weld Range is that we need a combination of iron ore types to form enough tons of iron ore to mine. So if we just had one iron ore type, generally we have high-grade iron ore, but it's present in not enough quantities for it to be economically significant. So generally these deposits are a hybrid type of deposits comprising multiple types of iron ore types. So we have successive fluid alteration processes superimposed on each other to produce iron upgrade of the BIF. So how does this translate to exploration strategies within Weld Range? Well, we now know that we've got 5 different iron ore types, and each iron ore type has very different physical and chemical properties. So, for example, the magnetite-rich ore is highly magnetic, obviously, and high density. So we can now start querying our existing databases, our geophysical database, for these types of anomalies. So, and we've also realised that this is our number one iron ore type within the district. So let's not waste time and money by searching for our less economic styles of iron ore. Let's put all our resources into putting it where it counts. Another thing is that we can generally use the iron to silica ratio as an index as a geochemical index for looking for these iron ore bodies. We can also note that hypogene alteration minerals are generally present in BIF, for example the carbonate alteration halo, but also in the surrounding country rocks. These mafic, igneous rocks generally have a alteration footprint, which are iron-rich hydrous minerals, such as chlorites, which we can identify in thin section, but also with spectral techniques using the analytical spectral device, HiLogger, and remote surveys such as ASTER and HiMap. And we're looking for perhaps the carbonate alteration in the BIF, or iron-rich chlorite and talc alteration assemblages. So in conclusion, there's 5 different types of iron ore types recognised at Weld Range. They can either form standalone types such as Beebyn, which is a big resource of residual magnetite ore, or else you can have hybrid deposits. An example is Madoonga, where in fact you need all of these to form a large enough ore body to mine. Each ore type has its own definitive physical and chemical characteristics, and this means that we can now be smarter in our exploration by targeting these iron ore types of greatest value. And so by their early identification, we can focus most of our resources towards their discovery. So for more information, either contact myself with our email, visit our webpage, a CET webpage, and our Iron Research Group web pages, and the contents of this presentation are also available in a lot more detail by looking at these two publications which have recently been posted online on the journal website. Okay, thank you. Thanks for listening.